Oh, okay, thank you. I'm Yang from Singapore Management University, but I just the proxy presenter for this paper, which is the collaboration for Peking University and the University of Hong Kong. And this work is entitled with Self-Supervised Graph Neural Network for Sequential Recommendation. And this work was also done by Yuxi, the first author, when she is intern at Hong Kong University. And the recommendation system have emerged as a crucial field for addressing the information overload issue, providing benefit to both users and service providers. And recent research have introduced graph neural networks to capture high-order relations over user-item interaction graph for encoding user preference. And sequential recommendation involves analyzing users' temporal interaction patterns and predicting their future behaviors. The advantage of self-supervised learning is to generate supplementary supervision signals from unlabeled data. So many existing work have motivated researchers to incorporate self-supervised learning into recommendation to enhance their performance. However, here's the motivation. Despite the significant progress made in graph and sequential recommendation with self-supervised learning, there are still several challenges. For example, like in this figure, the U1 and U2 have significant collaborative signals in the first period, but U3 has similar behaviors with U2 in the second period. Although some existing work has constructed dynamic and temporal graph neural networks, they typically overlook the consideration of both long and short-term aspects in graph neural networks. And they also fail to adjust the construction of a more robust dynamic learning paradigm. And secondly, the impressive results achieved by existing self-supervised learning methods heavily depend on high-quality data. However, real-world data often contains noise, such as the user's misclicks, temporal intent, such as the U2 adopting I3 in this figure, or some interest strips, such as the user 3 in this figure. And existing models tend to amplify such noises through multi-hop graph message propagation or multi-layer pairwise self-attention, which can greatly impact the representation of other nodes. And the notion of noise varies from different users, as some users have diverse interests while others have made stable preferences. For example, in this figure, the U2 has a stable tendency, and the user 4 with variable interests. And current denoising approaches lack the capability to effectively handle user-specific noise and often rely on random data augmentation. And in light of the previous challenges, this work proposed a self-supervised graph neural network, in short SelfGNN, for sequential recommendation. And SelfGNN aims to capture user interest by incorporating dynamic collaborative information and personalizing short-term denoising through self-augmented learning. And the proposed self-GNN is built upon three key paradigms. The first one is called short-term collaborative graph encoding, and the second one is called multi-level long-term sequential learning, and the third one is called personalized self-augmented learning for denoising. And I will introduce it one by one. And the first one is called short-term collaborative graphs. Dividing the global data into multiple short-term graphs based on the time interval, we can use the multi-layer light GCN to collaboratively propagate information, obtaining the short-term embeddings in each period for users and items. And then the second one is the multi-level long-term sequence. And the proposed self-GNN captures long-term user and item representations at a dual granularity level. And for each user's and item's short-term stage embedding, learn the dynamic positions using the GRU to construct interval-level time series. And based on the multi-head self-attention mechanism, obtain the interval-level long-term feature embeddings. And also based on the long-term feature embeddings of the items, we can learn the user behavior sequence through a multi-head self-attention mechanism, incorporating positional encoding, obtaining the user's instant level long-term features. And then the third one is called personalized denoising self-augmentation. And the proposed SelfGNN is further enhanced by this kind of personalized denoising self-supervised learning task. The term noise here refers to the temporary intents or misclicks, which cannot be considered as long-term user interest or new recent points of interest for predictions. And specifically, here the self-supervised learning task focus on filtering short-term non-inherent user preferences using long-term behavior patterns. And this design is based on the observation that users' behaviors may be motivated by short-term random interests. For example, a user who is not in favor of hiking but also may buy hiking shoes and energy drinks because of a one-time activity. And such noisy behavior data may disturb the modeling of the user's true interest in the long-term goal. And furthermore, we personalize the denoising self-supervised learning tasks with different strengths for different users, which caters to users with different level of interest variety. And for each training sample, we randomly select 2 observed user item age from each short-term graph, and then we compute the short-term and long-term similarities of each user and item as the following equation. And then the SelfGNN applies a learnable way to capture varying degrees of consistency in users' short-term and long-term preferences. And these weights are calculated using the presented equation here. And here the WTI determines the stability of the long-term score as a reference for correcting the short-term noise in the T's period. And then the SelfGNN analyzes the score differences between long-term and short-term views. And this self-supervised objective function is shown in this equation, where we can see that the D1 represents the similarity between ages in the long-term view, and D2 represents the score difference between ages in the short-term view. And then we exclude the backpropagation of the long-term score to direct the optimization process towards correcting the short-term score and learning the user's stability weight. And in this loss function, the role of the D1 is to guide the optimization of D2 in terms of direction and also the magnitude. And finally, this is the complete loss function consisting of the loss function for the recommendation task and also the self-supervised loss function. And then for the experiments are conducted on 4 open source datasets as shown in this table. And for evaluation, both positive and negative items are ranked together for each user, and we employ the hit rate and NDCG as matrix, and we evaluate the proposed model by comparing it with 18 baselines from 5 different research lines, including those conventional recommendation model, sequential recommendation model, traditional GNN, dynamics of temporal GNN, and also some self-supervised methods. And then we can see that the proposed self-GNN consistently outperforms all baselines across various evaluation matrices, and the superiority is due to first, integrating short-term graphs and long-term sequence information, and second, personalized self-augmenting learning framework that effectively handle noises in sparse short-term user interactions. And also, we remove each applied techniques for ablation study, which includes the following 6 variants as shown in the slide. And we can see that the full model of SelfGNN can actually achieve the highest scores across all datasets, indicating the importance of each component of the model performance. And then to assess the SelfGNN's robustness to the noise, we also replace the varying percentage of real interaction items with random fake items for all users. And in the right figure, we can see that the performance degradation under different noise scenarios. And in the sparse Amazon dataset, the search initially performs well with small noise amounts, and its performance drops sharply at 20% noise. And in contrast, the proposed SelfGNN is less affected by the noise than other models. And also, we do some sparse experiments as shown in the left figure. And also, there are some experiments conducted on those hyperparameters, including the 3 hyperparameters like the number of shortened graph partitions, and the dimension for user personalization weight, and the self-augmenting loss weight. And the performance initially improved with increasing the number of shortened graph partitions as the model captures more fine-grained information, but declines when this kind of number of shortened graph partitions becomes too large, making the graph excessively sparse. And that's all for the presentation. And if you have any question, feel free to contact the author. And thank you, everyone.